Well, thank you all for joining us today. My name is Jennifer Simmons. I am the current department head of the Petroleum Engineering Department at the Colorado School of Mines, and appreciate you all taking the time to join us today. For those of you that are here live and for those of you that will be watching this in the future, thank you for taking the time to review it. So what we're planning to do today is provide you a snapshot of some of the research projects that we currently have going on. Would like you to think in terms of the fact that they are very much a snapshot. We have a lot more going on than what we're going to talk about today, but we just thought this would give you a flavor of some of the work that is currently going on in our department and at the Colorado School of Mines in petroleum engineering. So for those of you that are live, we will be taking questions. We're going to save them for the end of the presentations. Each of the faculty is going to present for about 5 to 6 minutes, and then at the end we'll take those Q&A. If you do have something that might be quick, if you want to put it in the chat, we can respond to some of the quicker questions in the chat as we're going along, and happy to do that. So welcome to you all, and again appreciate you joining us. Again, I'm Jennifer Simmons, and I am your MC for today. So just a little overview of the department. Our current vision statement is shown right now. Petroleum Engineering Department's vision of distinction is to lead the world in education, training, research, and innovation for the responsible and sustainable acquisition and development of subsurface energy resources. And I think some of what you are going to see today is going to fit very well within that vision. Just to give you a couple of current facts, right now our enrollment in the Petroleum Engineering Department is about 290-ish undergrad students. We're running around 70 grad students that are working on research projects like you will see today. 12 and a half faculty. We don't have half a faculty, but we do have some part-time folks. And we ran close to $2 million of research last year. And something that we're happy to tout and trying to get the word out a little bit is petroleum engineering at the Colorado School of Mines will be 100 years old in 2022. So look for some upcoming events and thoughts on that particular thing next year. Getting more close to home on the research front and what we're talking about today, here is a listing of some of our research groups. We have a variety of research centers specializing in a lot of different areas, anywhere from reservoir considerations, through stimulation, through modeling, through drilling. And we don't just do research through our research groups. We also, many of us have individual research projects that are individualized to a specific company or individualized to a couple of companies or people that want to look at certain topics. And we're always happy to consider these areas that we might be able to help out with. So without further ado, I'd like to introduce the panel that we will have today, and you'll be hearing from each one of these folks. We have Dr. Louise Zerpa, Dr. Erdal Ozkan, Dr. Yishu Wu, Dr. Shalong Yin, Dr. Hossein Kozumi, and Dr. Tedesse Teclu. We'll all be presenting, like I said, a little bit of a sample of some of the work that they're doing. So with that, our first speaker today is Dr. Louise Zerpa. And so Louise, I will turn it over to you.
Thank you, Dr. Simmons. And I'm presenting a work that we're doing in conjunction with the Geophysics Department. In our group, on our research, we are combining experimental work and modeling work to study multiphysical properties of rock fluids and their interactions. So what you're seeing here is an example of that, where we're doing the experimental work and modeling, and to work on an application related to the development of a petroleum field. Next slide, please. So in this project, we have this combination of multiphysics measurements to detect the phase transitions during fluid flow in reservoirs. So this is a particular example for undersaturated oil reservoir in the Barents Sea, where they wanted to do a water flooding process, but the temperatures are so low in that region, and it's a cold reservoir, that gas hydrates may form. So we needed to detect the formation of these solids during the water flooding process in this reservoir. In the next slide, we have the equipment that we were using. So first we start doing an assessment of the properties and behavior of the reservoir fluids. And for that, we use the facilities in the PVT lab in Marcus Hall. And where we're seeing here is a high pressure PVT apparatus where we take the crude oil, the dead oil from the reservoir, and we recombine with natural gas to form a representative reservoir fluid for the reservoir conditions. Then we do a displacement experiment in a core. So we do a core flooding experiments. And what we're seeing in the picture in the middle is a picture of the core. We have a 3 inches in diameter core with 10 inches in length. And we put a series of sensors to detect the formation of these solids. These sensors are acoustic or ultrasonic wave velocity crystals that we put in different places. In the core, we have strain gauges, electrical conductivity rings, and temperature measurements. And then we see a diagram in the right figure that is the core flooding apparatus that we built in order to perform this experiment. In the next slide is just a summary of the results that we got. We were able to detect the formation of gas hydrates in this oil reservoir at 4 degrees Celsius with no flow. But when there is a water flooding, with this water injection, the hydrates form at a warmer temperature, 7 degrees Celsius. The temperature of this reservoir is 17 degrees Celsius, and the injected water is at 2 degrees Celsius. So we can cool down this reservoir to the point that hydrates can form, and they will affect the permeability. What we're doing now, or our next stage, is to do a multi-scale modeling study of this process, where we're looking at the pore scale. We're seeing here a CT scan image of the core that we were using, a sandstone core. We're doing modeling at the lab scale to match the experiments and to calibrate our model based on the experimental observations. And then we're doing the upscale to the field size, to the field scale, in order to design the exploitation strategy in this reservoir to prevent the formation of hydrates or solids that can reduce the permeability and improve the productivity from this field. And so this is the example from our group, and thank you for your attention. I will be glad to take questions later. Thank you, Jennifer.
Thank you, Louise. Appreciate it. So next up, we have Dr. Erdal Ozkan, who is going to talk about some of the work that he has going on. And again, if you do have questions, we'll handle them at the end, or you can, if they're quick or something, you can put them in the chat. So thank you. Erdal, all yours.
Thank you, Jennifer. This research project I'm going to introduce is a joint project with Dr. Shailong Yin. Next slide, please. Our problem here we are addressing in this research is the well-known low recovery issue in tight oil plays. And especially these days with the current economic, financial, and social, political landscape, it has become a more important problem, of course. But to address this issue, we have been using gas injection, and there are a lot of projects going on. This is at the pilot implementation phase in the field, and it's one downside of the implementation today is the fact that most of the current approach is based on the experience in conventional plays. So here our objective is to look at the EOR mechanisms in tight oil plays by gas injection, and also develop some appropriate models to predict the performance of such projects, which is extremely important if you are pursuing such an opportunity. Next slide, please. Okay, the highlights of the problem may be seen on this slide. I'm not going to go through all of them, but the main idea here is that the problem is caused by the stranded oil in tight matrix. And because we are talking about nanometer scale pores, we can think about a filtration mechanism where heavier hydrocarbon molecules are stuck in the system. And the other aspect which makes it completely different from the conventional systems is that there is no bulk displacement, or in general what we call flooding type of project here. So gas injection works by altering the flow at molecular level. And also one more misperception here is that gas injection is gas injection, no matter what type of gas you use, which is not necessarily true. Different gases may trigger different mechanisms. So our goals here, first of all, to find out stranding mechanisms in a tight matrix, and then we define it as a hindering process, which basically keeps the oil stuck in matrix. So we try to hinder, we try to incorporate this hindering mechanism into our modeling. And then we try to explore absorption and slowing of diffusive mechanisms by using experimental and modeling techniques. And in the end, our objective is to come up with a complete hindered transport model for enhanced oil recovery. Next slide, please. So some results of the research, these are just partial results, of course. There are two key mechanisms found out so far. One of them is the absorption, and the other one is the slowing of the diffusion in the system. And we have found out that CO2, for example, targets more of the absorption phenomena, and produced gas injection, which is more common these days. It basically works by targeting slow diffusion in the system. So based on this, we definitely think that higher injection pressures are important, useful, but we are not that keen about this minimum miscibility pressure discussion, because it's not a displacement process here. And also this is a relatively thin layer on the surface of the matrix, which should be taken into account in the design of these projects. And one of the important findings is that when you inject a multi-component hydrocarbon into these systems, individual components of hydrocarbons will have some slowing effect in the mixture, especially heavier ones. And that is basically the cause of hindrance we are looking at. So our current status is basically we are determining, measuring some process parameters, and also we are developing compositional hindered transport simulator to be used for design. That's all I want to share for now. If there are questions, we can discuss later on. Thank you.
Thank you, Dr. Ozkhan. Next up, we have Dr. Yishu Wu, who and a slew of people contributed to his, but I will let him talk a little bit about that. So Yishu, you are up. I think you're still on mute, so you might want to.
Okay, thanks, Jennifer. We have a modeling group called Energy Modeling Group, and me and Dr. Phil Winterfield, and also we have about 10 graduate students plus some postdoc per year. Okay, next slide, please. Yeah, this modeling group, EMG, was built, I think, in 2009, about 11 years ago. Really, the purpose really is develop and apply state-of-the-art reservoir simulation technology for research, teaching, and application. In the area, a little bit broad energy area, subsurface resources, and environmental application. Next slide. What we have done with some impact research result included here. We have developed a number of tight oil and shale gas reservoir simulators. And in this area, modeling thermal hydrologic and geomechanical or geochemistry coupling part, I think we are the leading force. I don't think a commercial software can do fully coupled on these physical processes. Then also we work in recent years, like 5 years, we have developed a really very efficient multi-physics model for CO2 EOR operation and CO2 geosequestration. And also we have done some multi-stage hydraulic fracture modeling, improve current industry technology by include the stress shadow effect and also thermal effect. So that's some contribution from this group. Next slide. The particular simulator we talk about for TED oil, we have MS flow comp, which is the isothermal model component, TED oil reservoir simulation model, which is coupled geomechanics and also nanopore size confinement together, fully coupled. The next one, MS flow CO2, which we just published a paper in SP journal like a couple months ago. This one is really incorporate additional geomechanical coupling, pore size, nanopore size confinement, capital pressure confinement, and also thermal effect for CO2 flooding, CO2 or half puff. The next simulator we developed is we call SunGas. This is for really shale gas reservoir with some weakly geomechanical coupling for shale gas reservoir simulation. Then also we develop, this is funded by DOE through 2 projects over the past like 10 years. We call TOP2 CSM for CO2 sequestration. This one, in my opinion, is most advanced reservoir simulator in the world for CO2 geosequestration in brine aquifers. Actually, we have THMC coupling fully. Then also we have some DOE project sponsored TOP2 EGS. This is for enhanced geothermal system simulation. So with fully coupled geomechanical chemical reaction simulation. The multi-stage hydraulic fracture simulator we call this FRAC CSM actually, sorry, FRAC CSM. This one is for multi-stage hydraulic fracture simulation. We incorporate the stress shadow effect by calculating the stress change actually, and also a thermal effect. The optimization by FRAC OPT is really optimize this FRAC CSM for optimal design, real-time simulation actually, we apply to the field. So for future research and collaboration with our alumni or companies, I have some idea here. I think we can do a lot of modeling studies for optimal design, half puff or natural gas CO2 flooding calculations. We published quite a few papers recently, actually. And also on the CCUS front, I think the certain lack research in use developed oil gas reservoir for storage, especially unconventional reservoir for storage. I think this part could turn on some research project. Then the final one, I think we would like integrated modeling of help or exercise for optimizing fracking operation design. So with the TED oil reservoir conditions and TED reservoir conditions. Okay, thanks. You will have some questions. I'm happy to answer later. Thank you.
All right, thank you, Dr. Wu. So next up, we have Dr. Shilong Yin, who you've heard a little bit about already, and he's going to talk about some of his projects now.
Thank you, Jennifer. You can forward. All right, thank you, everybody. Thank you, alumni and our industry partners. The snapshot that I'm going to talk about today is on relative permeability of multi-phase flows. For us doing reservoir management work and reservoir simulations, we know that relative permeability is an important property This is actually not a constant as we usually consider as a function of saturations. Relative permeability actually varies with the flow condition. And that's the topic that we're quite interested in and want to investigate. Another motivation of this is that relative permeability, we all need this property. The way to do it is to perform a special core analysis scale. But a special core analysis is actually quite difficult and time consuming to do for unconventional cores. So our objective is to predict the relative permeability using multi-phase fluid mechanics. And then we're gonna use data that are easier to obtain. So we can use porosity, permeability, and we can use mercury injection data. And using this data, we want to construct a relative permeability and let it vary with flow condition. So next, please. So we cannot do a slide without equation. So I put a very simple one up there. The important parameter is the so-called capillary number. So in a tight reservoir, wettability, surface tension is important, and that controls the relative permeability. So that parameter is implemented in that dimensionless parameter called CA, the capillary number. So talking about our approaches, we would like to predict relative permeability using theoretical model based on bundles of capillary tubes. The reason why we want to use this model is that it can give you prediction on capillary pressure on relative permeability in a matter of a few seconds. It's very computationally efficient. To prove that the theoretical model work, that's actually the harder part. We do microfluidic experiments. I'm going to show a few examples next slide. And for conditions that are difficult to do in experiments, for instance, if we want to consider pressurized carbon dioxide interaction with oil, that's an experiment that is difficult to do in the lab. We also use computational fluid dynamics to supplement the experiments. So the middle 2 points there basically used to investigate situations where we have perfect pores and perfect conditions. And then in the end, we do core experiments to show that in reality, these theoretical models are going to work. So next, please. So Jennifer, if you just click on the water, oil, and surfactant, we'll let those movies play. Does it play?
Doesn't look like that one's playing.
Well, that's okay. I guess the files are not inserted there. So anyway, so those two just illustrations to show you how microfluidics experiments look like. They're basically controlled pores and controlled processes. And then we have an animation for CFD simulation of fluid flow through porous media. That one does play. And then there's an illustration of a bundle of tubes model. Right now, we're mostly developing models for high permeability cores, but we're moving to set up models for tight reservoir cores. Thank you. This is all I wanted to share with all of you today. Be happy to answer questions later.
Thanks, Shalom. Sorry about that video. We must not have gotten the file. So next up, we have Dr. Tadesse Teclu. So Tadesse, all yours.
Okay, thank you, Dr. Miskins. My name is Tadesse Teclu, and I'm a research assistant professor here at the PE department. My research works include EOR, IOR, and fluid, rock fluid interaction, relative permeability, capillary pressure, reservoir fluid properties, etc. measurements. matrix fracture permeability characteristics, and geomechanics study, CO2 sequestration, and geothermal reservoir. And all those experiments I do at high pressure and high temperature conditions and at varying stress conditions. Next slide, please. Here I'm showing one of the studies we did. It's an EOR experiment work in carbonate reservoir using combination of different injection fluids. The reservoir is a tight carbonate reservoir, about 1 millidarcy from Middle East. It's a UAE offshore reservoir. We perform high pressure, high temperature core flooding experiment, first using seawater until no more oil is produced, and then followed by different concentration, low salinity water flooding, EOR, followed by a low concentration surfactant flooding, EOR, and finally using CO2 EOR. And also we perform contact angle, as you can see it in the side, contact angle measurement, imbibition experiment, interfacial tension study, zeta potential experiment, and other relevant experiment for this specific reservoir to understand fluid rock interaction, wettability alteration, and understand the EOR, IOR process in this specific reservoir and also in other reservoirs. We also do compositional modeling using CMG or other softwares. I also do experimental and modeling work in very tight shell reservoirs using CO2 half and puff EOR studies. Next slide, please. In addition to EOR, IOR experimental and modeling work, I also do experimental studies of matrix and fracture, permeability and geomechanics studies with and without propellant. These studies are at high pressure and high temperature and at varying stress conditions. And we investigate matrix and fracture permeability and geomechanics before and after rocks interacted with different fluids, such as using low salinity, low concentration hydrochloric acid to investigate acidizing in carbonate and carbonate-rich shell reservoirs, also matrix and fracture permeability and geomechanics study before and after rocks interacted with slick water and drilling and completion or hydraulic fracturing fluids, and similar permeability and geomechanics studies in fracture geothermal reservoirs for CO2 sequestration process and similar concepts. So those are the research I'm working on. Thank you very much.
All right, thank you, Tesas. And so batting cleanup for us. It's my pleasure to introduce Dr. Hossein Kozumi, who's going to speak a little bit about some of his work.
Good day, everybody. I'm going to start with this statement that population is increasing at a rapid pace, and there will be continued need for food, clean water, clean air, and energy. Thus, I believe hydrocarbons, oil and gas, will continue to fuel the energy needs for decades to come. However, we have to adjust to the public pressure and in reality, the needs of society. Thus, I have adjusted my research program to address these issues. And these are, I stated, number one is EOR in conventional and conventional reservoirs, carbon capture and storage, geothermal energy, and hydrogen as fuel to store energy. I have 8 graduate students currently and 1 postdoc who was not a student before. So that's the introduction to what I have 3 slides just to exemplify what my efforts look like. Dr. Simmons, could you give me the next slide, please? So the three projects that I chose, one was cost-effective chemicals, and number two is carbon capture and storage in conventional reservoirs. And so this consists of two different things, you know, the latter one, because it's conventional and conventional. So one of the major issues in the world is just that, first of all, EOR, it contributes only a very small fraction to the world oil production. Is about maybe at best 1.5%. But nonetheless, so far there have been a lot of very expensive, you know, chemicals have been used, but for the last, I would say, 5 decades. We can actually do better than that. We can use a lot of low-cost chemicals. These are some simple classes like ketones. Ketones are like acetone that people use to, or ladies use to remove nail polish and things like that. And non-ionic surfactants, which are just some sort of, looks like soap. We can use this one both in conventional and conventional reservoirs. That's one area that, you know, we do research nowadays. And number two, CO2 from waste to energy from cement plants and natural gas and coal electric plants can be captured and utilized to improve oil recovery and sequester the entire CO2. And then the road ahead is challenging. But CCS, which is carbon capture and storage, is increasingly one place to make significant necessary contributions to the net zero emissions that, you know, that is required or people are pushing toward. So if we go to the next slide, I'll give you an example of what we are doing. First of all, in regard to conventional reservoirs involve injection wells and production wells. And there is a lot of issues with the conformance of, and so you can see that on the left slide and the middle slide. So these are one of the examples of the type of work we have done in the past. The slide on the right, which doesn't have any color in it, exemplifies the nature of the unconventional reservoirs with multi-stage hydraulic fracturing, where the hydraulic fractures, they really create a lot of macro fractures and macro fractures. Now, in unconventional reservoirs, for EOR, you inject and produce from the same well, while in conventional reservoirs, you inject from one well and you produce from the other side. And in this one, whatever you inject, it has to contact the surface of all those macro fractures to extract oil and bring it back up. But anyway, that's the basic philosophy that we use. May I have the next slide, please? Yeah, this one basically is really, you know, the essence of the whole thing. There is already, you know, in the last 25 years, there have been a lot of effort on carbon capture and storage. Of course, when we talk about CO2 or that's carbon capture utilization and then storage. So CCS becomes CCUS. But also, people have worked on this, and currently there are 13 projects worldwide that they are capturing CO2 and they convert it to liquid, and then they send it to storage. These are saltwater storage reservoirs. However, we would like to do the same thing, but we convert that one to EOR. So the picture on the right is called the Northern Light Project in the North Sea You can see from Ireland, England, all the way to, Scandinavian countries. That's what the process is. This particular project is continuing, and by 2024, we will have 69 completed projects. Anyway, that's the basis of the excitement, and I call it aspiration. The aspiration for really cleaning up the air by capturing the CO2 and putting it in the ground and still improve our recovery. Thank you very much, and I'll be glad to answer any question down the road. Thank you.
Thank you, Dr. Kozumi, appreciate it. So yeah, so we're ready for some questions now. And as we start to handle some of the questions, I'm just going to pull up this slide, mainly because if you want any follow-up information, our webpage, our website is listed there, and you can find any of us listed in that area under the faculty if you want to follow up with some of it. So I'm going to start off with Dr. Ozkhan. You answered some of this in the chat, but I'm going to give you a chance to speak to it a little bit. Will your work investigate hydraulic fracturing reservoir rock? Field experiences have resulted in injected gas traveling large distances, sometimes off lease, with minimal pressure increase due to the created fracture networks. Are you looking at some of that, or you want to go ahead and talk a little to that?
Yes, of course. This is one of the major problems in the implementation of gas injection. It is not a secret from the beginning that a lot of people have been reporting that injected gas shows up in the nearby wells almost immediately. So this raises concerns about the viability of these types of approaches. We have been looking at this, and I must upfront say that this is one of the realities. Some of the things you cannot change. It is going to happen. But how do you limit it or restrict it? This is most probably an implementation issue. So instead of just looking at it on a well basis, if you just look at it as a pad or as a multi-well injection system, then you can see that you can even convert this into your benefit, because in this case, your idea is basically to soak a larger area with CO2, and then during the puff period, you want to produce from these wells. And this and a containment wall strategy around this area may actually convert this into a successful project, so you don't worry about the conformance issues as in the conventional sense, such as, for example, if you increase the pressure to meet the minimum miscibility pressure in the field, you definitely increase the injection rates, and at the same time, you increase the velocity of the gas in the fracture network, so your conformance is going to be bad. But in general, all these concepts need some good modeling capabilities. So that's what we are also working on right now.
Great, thank you. The next question I'm going to give to Dr. Wu. Yishu, you've spent a lot of time with geothermal modeling. So are you using CMG stars for performing geothermal simulations? Have you investigated the merits of closed loop geothermal systems that rely on conductive heat transfer? And if so, what's your opinion of the viability as compared to enhanced geothermal systems?
Okay, thanks. For most modeling study, we use our own code, top2 EGS, but we did use star to benchmark some of the calculation from top2 EGS during the development stage, like 7-8 years ago. The concept used to inject the producer, right? Concept to produce geothermal. I think it's not very efficient, seems to me, because it's variable transfer problem, right? Heat transfer problem. I saw some of the presentation a couple of years ago at Stanford geothermal workshop. Yeah, you can get a little bit just the delta T is small, like 30, 40 degree. It's just not very efficient. I don't think it's, unless you have very, very long borehole. By long, I mean 10, 20,000 meters, maybe. But anyway, 1,000 meters. Otherwise, by conduction alone to produce heat is not efficient because it's slow. So that's my opinion on the
Great, thank you. So the next question, let's go with Dr. Kozumi. This is an interesting question. I think a lot of people are interested in. Many in the public and others are beginning to fear carbon. Do you have any thoughts on the future for fossil fuels? Will they become unacceptable due to environmental impacts? And my personal view, this is from Mr. Perry, is that we do not need to fear carbon, rather manage carbon.
Well, actually, I do agree with you. We need to manage carbon. For instance, we are actually flaring about 5 to 6 trillion cubic feet of gas every year. If we take those things and directly inject them into the same reservoirs they produce, they can actually enhance recovery without creating 5 or 6 trillion cubic feet of CO2 in the atmosphere. That's one example of managing carbon. Another thing is just that there are about 1,400 natural gas power plants in the United States. I calculated for Colorado, for 5 power plants, we emit equivalent to 450 million cubic feet of CO2 per day. Now just imagine, in DJ Basin, if we take those things and inject them in petroleum reservoirs, we can sequester them. And also we have reduced 450 million standard cubic feet per day of carbon emission. I am really excited. I think with this CCS program, we can actually continue using fossil fuel to generate energy for our economy, but at the same time, we can actually clean up the air. There are other issues. There is not much time at this point to discuss, but I'll be glad maybe at another time to discuss a lot more salient issues. Thank you.
Great, thank you, Dr. Kozumi. So we've got the videos that Dr. Yin was trying to play earlier. So we're going to, I'm going to hand it back over to him, and we're going to see if we can play these videos. So so long, I'm not sure which order they were in, but
That's okay.
WF, is this okay?
WF means water flooding.
Okay.
So this is basically an experiment in a microfluidic model. Water flooding is highly heterogeneous. You leave a lot of oil, which is transparent behind. Water is colored.
And then let me see if I can pull up this second one for you.
Right. This is a surfactant flooding. And you can see that with the reduced interfacial tension, you leave much less oil behind. And apparently the relative permeability of these two processes shouldn't be the same. That's all. Thank you, Jennifer, for bringing them up.
Of course, yes, absolutely. So I'm going to stop that one. We had a couple of pre-questions that came in that I want to get to, and then Darian, I see your other question. We'll come back to that. This one I'm gonna toss this to Dr. Kozumi. Let's go with you. Do you see that if there are crossover opportunities between geothermal energy development and the petroleum industry?
Absolutely. You know, we are very knowledgeable in drilling holes, and especially with all the experience we have with unconventional reservoir multi-stage hydraulic fracturing. You know, of course, Dr. Simmons, you know that you and I are involved. Hopefully, we're going to really make this one a reality, that we can, you know, take horizontal wells in granite and place multiple hydraulic fractures to create, you know, heat exchange surface area. Then we can inject, you know, cold water from one well and produce from another well parallel to it, which has got frac hit. The fractures, they hit the production side. And then they create the so-called the surface area for heat exchange. So it becomes underground heat exchange. So you can capture tremendous amount of energy. You can bring it to the surface. You flash it on the surface to steam. Automatically it becomes, you know, flashes to surface to a steam. You can run the turbines and generate electricity, and it's a very clean form. So I would say yes, geothermal would be part of the mix for us, and we can transfer a lot of our technologies to that area.
Thank you. Dr. Wu, do you want to weigh in on any of the geothermal? Because you've spent quite a bit of your time working on that too.
Yes. Currently, I think the geothermal, especially EGS, enhanced geothermal system, rely on the technologies used developed in the petroleum industry, right? Just to add to what Dr. Kozumi has mentioned, anything from drilling, completion, fracking, to recovery, the inject fluid, everything. I think the technology really rely on everything we do. We know how to do it. So I think the most important industry to support geothermal in the future is petroleum industry. And also in terms of total amount of energy, I think geothermal is most important future energy in addition to solar. Solar geothermal pretty much answer the future energy to human being. You talk about 100,000 years. Okay, thanks.
Okay. Thank you. So I'm going to come back to Darian's question in the chat then, because this ties into this particular topic a little bit. Perspective, can we provide any perspective on the recent announcement about 4 faculty positions at mines that are soliciting in renewable energy areas, specifically power systems? Will any of these be in the Petroleum Engineering Department? And if so, which ones? The future of creating renewable energy engineers in mines. So the really quick answer is mines is still hiring faculty in certain departments, but we are also looking at what are known as cluster hires. The clusters being that these are people that specialize in an area that will have a home department, but can work interdisciplinary between different departments. And many of us already work interdisciplinary, there's no doubt about that. But some of the topics that we are looking at these cluster hires for really lend themselves to a very big focus on interdisciplinary work. So the question, will any of them be in Petroleum Engineering Department? Possibly. There are many departments that are participating in this search. The idea is to get the top 4 people that we possibly can. And then depending on where their real expertise lies will depend on which department that they get situated in. The future of creating renewable energy engineers, I think you've heard a little bit about that already. We have a lot of skills that tie into other areas, specifically things like geothermal, like Dr. Kozumi was saying. We have to, the skills are very transferable. The skills are transferable in CCUS and CCS. So in a way, we're already creating some of these. It's just a matter of, you know, where they go to work and what future topics they work in. So that's kind of where that particular situation stands. We also have a cluster search right now going on in data analytics. And there's a chance that somebody from the data analytics cluster will end up in petroleum also. We'll just see how it plays out. So the question that comes next, these are some of the preliminary questions that came in, and I know we've only got a few more minutes for Q&A, but one, I actually don't know who to hand this to. So if anybody is willing to answer this one or needs, is anyone working with nanosurfactants, possibly in conjunction with CO2 or nanosurfactants areas? So, okay, Dr. Kozumi, I'm going to give that one to you. Anybody else that wants to weigh in, please do.
Well, nanosurfactants are metal oxides. They have got particle size of approximately 10 to 20 nanometer in diameter. We have spent a lot of time looking at nanoparticles. There are much simpler ways to really enhance recovery than nanoparticles. While nanoparticles can be helpful, I don't think that's the way to go. So that's my answer to it. There are better ways to do that. Thank you.
Thank you. Anybody else working in that particular area that wants to weigh in? Okay.
I can say a few things also just to add up to what Dr. Kozumi mentioned. Every time when you talk about surfactants, you're talking about some microemulsions also. So it is not just the size of nanosurfactants here. It is the size of the microemulsions you create. And if you are thinking about these nanosurfactants for applications in unconventionals, I think I can safely say that there is not much hope in that direction. But there may be some other applications here and there, but at the end of the day, it's an economic game. So you need to look at the project economics. Unless there is a cheaper option, these more advanced technologies can be taken into consideration.
Thank you. So we're going to handle one more question out of the pre-existing ones, and this is because it kind of launches into some of these future research showcases like this we might have. We had some questions about any work that's going on with fiber optics and fiber optics cables. We actually have quite a bit of work that's going on with fiber optics cables right now. We have some liquid loading and production logging work that is going on with fiber. And we also have a project up at the Edgar mine that many of you as alumni know about, the mine that the mines owns up at the Edgar. We are drilling a well there. We have drilled a well there, and we are instrumenting wells that run through the rock and create full circuit loops that are going to be instrumented with fiber optics to allow us to study, again, fluid flow and horizontal well systems, but it also allows us to study some areas like strain behaviors and even acoustic behaviors because of the ability to have explosives up in that area. So the reason I mention that is because this particular research showcase is the first of what we hope will be many over the next several years. We are planning to do this twice a year for right now. Depending on response, we might even do it more often than that. But what you saw today were some of our more what you would consider possibly reservoir engineering projects. Look for some announcements down the road where you're going to see some more production oriented and projects, things like some of the fiber, some of our drilling applications, some of our stimulation applications, and some of the other areas that we have work going on. So we'd like to thank you all for taking the time to join us today. We greatly appreciate it. No, in Houston, it's lunch hour for some of you, so thanks for sharing your lunch with us, and we appreciate it. Thank you. And any follow-up that you want, I guess I should say follow-up that you want, please email any of the panelists. They'd be more than happy to talk to you about that some. So thank you. Appreciate your time.